Over the last few lectures, we have been talking about the mathematical details behind the WKB method and some of its basic consequences. Let me just remind you that the WKB method essentially uses a sort of approximation beyond the free particle, where the wave function is like that of a free particle, except that instead of e to the I px by h cross, what you have is I by h cross times integral of p of x prime dx prime. This particular equation can also be extended beyond the classically allowed region. In the classically forbidden region, where v of x is actually bigger than the energy, the classical momentum becomes purely imaginary, which is why classically this is a forbidden region. In such a situation, the WKB wave function picks up an extra I, which in addition to the I in front already, ends up giving you a purely exponential wave function. In today's lecture, what we are going to do is talk about a few applications of the WKB method. But before we do that, let me introduce, or rather reintroduce you to some abbreviations that we are going to use extensively that will simplify our calculations a bit. In the classically allowed region, it is obvious that square root of twice m e minus v of x, the quantity that sits within the integral of the exponent in the WKB wave function, is nothing but the classical momentum, and we obviously write that as p of x. The abbreviation I am referring to is W a comma x, which essentially is the phase factor sitting in the exponent. We use the abbreviation W a comma x to stand for this quantity, 1 over h bar, the integral from a to x of px prime dx prime. Let me point out that this function is an increasing function of x for the simple reason that p of x prime is positive throughout. Note that although I have been talking about p of x as a classical momentum, this is strictly speaking correct only when the particle is traveling to the right. Since p of x is a square root, it is a positive quantity by definition. So when the particle is traveling to the left, its momentum really is minus p of x. Now, what the WKB approximation tells us is that in the classically allowed region, the wave function can have two components. e to the iwa comma x by square root of p. Let me remind you that the square root of p comes from a slightly improved or higher order approximation that we carried out in deriving the WKB approximation, times some coefficient a, plus e to the minus wa comma x by square root of p times some other coefficient b. Note that changing the first argument a in wa comma x, which essentially is changing the lower limit of the integral involved, simply shifts wa comma x by a constant, and the effect of that can be absorbed within the arbitrary constants capital A and capital B. So in a sense, small a can be chosen somewhat arbitrarily. However, it is often convenient to choose small a to be the location of a classical turning point, and that is usually the way in which we are going to use it. It is easy to interpret these, especially if the potential becomes steady very far away. e to the iwa comma x essentially behaves like e to the ipx by h cross, a right-going wave, and e to the minus iwa comma x behaves like e to the minus ipx by h cross, which is a left-going wave. Now, this is something we are going to need when we want to interpret scattering results from a barrier. Another important, though rather obvious point is that if you were to interchange the two arguments, so use x comma a instead of a comma x, the quantity W will simply change sign. Let us now turn to the region where the potential energy V of x is bigger than E, the so-called classically forbidden region. In this region, P of x, the momentum, becomes purely imaginary, so we give up on that and use a slightly different but related quantity P bar x, which is square root of twice m V of x minus E. And in place of W of a comma x, we now have W bar a comma x, which is 1 over h cross, integral from a to x as before, but of p bar x prime dx prime. And just like W of a comma x, W bar of a comma x is also an increasing function of x, and it's positive whenever x is bigger than a. Now, the WKB wave function in the classically forbidden region takes the following form. E to the power minus w bar a comma x by root over p bar is one term which is multiplied by its constant capital A. In addition, you have another term which is e to the plus w bar a comma x by root over p bar times some constant capital B. Now, the increasing or decreasing nature of these exponentials become very important, both for physical reasons, because we want our wave functions to stay bounded and not blow up, but also because of the fact that the way in which an exponential function in the classically forbidden region connects to a sinusoid in the classically allowed region actually depends on whether the exponential is a decreasing exponential or an increasing exponential. And in this case, let me warn you that when we say decreasing or increasing, we mean decreasing or increasing as you move away from the turning point. This is slightly different from the standard calculus sense of the word decreasing or increasing, where you mean that a function is decreasing if it decreases whenever x increases. Now, if the forbidden region happens to be to the right of the turning point, as you can see in the picture here, the potential energy is more than E when you are to the right of the point x equal to A, the turning point. In such a situation, our standard calculus notion of the words increasing or decreasing actually matches what we mean here. So, e to the minus w bar a comma x is the exponentially decreasing function as x goes to larger and larger values away from a, and e to the plus w bar a comma x is the exponentially increasing function as x becomes larger and larger away from a. And now, though this is rather trivial, it's actually quite important to be careful about this, so I'm going to stress this point. If the forbidden region happens to the left of the turning point, can still write the WKB approximation for the wave function in exactly the same manner as before, but it is perhaps better or more convenient to write it in the form that is being shown here. That is, instead of using e to the minus w bar a comma x, you write e to the minus w bar x comma a and e to the plus w bar x comma a. Notice that here w bar x comma a is positive simply because x happens to be less than a because you are, remember, in the forbidden region, and here the forbidden region is to the left of the turning point. More importantly, as x goes more and more deeper into the forbidden region, that is further and further away from a, so x goes to smaller and smaller values actually, w bar x comma a increases in magnitude and e to the minus w bar x comma a becomes a decreasing function, decreasing as you move away from the turning point. Now this is going to be very important in our discussion about the connection formula, which is going to come next. Before we go on to discuss the connection formulas, let me remind you about why we need them in the first place. For this, let us recall the condition for validity of the JWKB approximation that we talked about in the first lecture on this topic. The WKB approximation essentially was an approximation in powers of h bar. So you had h bar to the power 0, phi 0 plus h bar to the power 1, phi 1 plus h bar to the power 2, phi 2, and so on. And the condition that we had derived, at least one of the conditions, was the rate at which phi 1 prime, the first order correction, grows must be much smaller than the rate at which the phi 0 grows. So h cross by 2 p prime by p turned out to be much less than p. Now one way to rewrite this expression, which is going to be quite useful in many applications, is to simply say that this is the derivative of h cross by p, and this must be much smaller than 1. Of course, there could have been an extra factor of 2 put in here, but since we are talking of values which are much, much smaller than 1, an extra 2 here or there really does not matter. And using the fact that dp dx is related to the force by dp dx equals dp dt, the force, times dt dx, you can easily show that the expression becomes h cross mf by p cube is much, much less than 1. So, the WKB approximation is valid wherever the force is much, much smaller than p cube in this sense. And this works as long as the potential energy is a slowly varying function, because remember, the derivative of the potential energy is exactly what the force is. But one place where this formula is definitely not going to work is where p vanishes or becomes very small. So the WKB approximation is clearly violated near a turning point. And this should not come as a surprise, because the 1 by square root of p or 1 by square root of p bar, which you have in the WKB wave function, diverges whenever you are close to a turning point. So the situation is like this. You have a decent approximation in the classically allowed region. You have another kind of decent approximation in the classically forbidden region. But you cannot really match these solutions directly, because the boundary of these two regions happens to be the turning points where the approximation breaks down badly. So what you need are connection formulas which allows you to connect a solution on the left to a solution on the right of the turning point. We have already discussed in the very first lecture how to do this. We had talked about linearizing the potential in the immediate vicinity of the turning point and taking the solutions of this problem, which turned out to be the ID functions, and using their asymptotic behavior to match the solutions on the two sides. The mathematical properties of the ID function and how to find out the asymptotic behavior essentially occupied us over the last two lectures. But what we need really are the final results, which are how the exponential solutions on the classically forbidden side connect up with the sinusoidal solutions on the classically allowed side. Let us now quickly recapitulate the connection formulas themselves. It is possible to write down a connection formula which will work both when the forbidden region is to the right or to the left, and that is what we are going to do as a summary after a while. But it is perhaps easier to understand and also easier to apply in situations if we think of these two cases separately. So first, let us consider a case where the forbidden region is to the right of the turning point, as is shown in this particular figure. Here, the decreasing exponential is obviously e to the minus w bar a comma x, and that connects to cosine of wx comma a minus pi by 4. Of course, the 1 by root over p bar on this side becomes 1 by root over p on the other. And what is very important is that there's an extra half which is sitting with the decreasing exponential on this side. Of course, you could also say that you have a 1 here and a 2 on this side. It's just a matter of connecting the two results properly. The increasing exponential, on the other hand, is e to the w bar a comma x with a plus sign by root over p bar, and that connects to sine of wx comma a minus pi by 4 times 1 by root p with an extra minus sign. Let me point out that on the left hand side, we have deliberately written wx comma a instead of wa comma x, because here, x being less than a in the allowed region, wx comma a is positive. What really should go inside this formula is mod of wa comma x. So we have chosen wx comma a specifically for that reason. For the other kind of turning point, where the forbidden region is to the left of a, on the left you have a decreasing exponential which, as I just pointed out a while ago, is e to the minus w bar x comma a. And again, this is the one which comes with a half and which connects to cosine on the other side, cosine of wa comma x minus pi by 4. Note that here we are talking of wa comma x because here the classically allowed region is to the right of the turning point, so x is bigger than a and wa comma x is positive. The decreasing exponential behaves this way. The increasing exponential, on the other hand, is e to the plus w bar x comma a, and that connects to minus 1 by root p sine of wa comma x minus pi by 4. So to summarize, in a scenario like this, where the energy is represented by this horizontal red line and the potential energy by this blue curve here, you have a classically allowed region between this and these two turning points, and beyond that you have classically forbidden regions on both sides. And in the classically forbidden region, the wave function is basically of the exponential kind, both on this side and on this side, and you will have a sinusoidal wave function in between. And if the forbidden region extends to infinity, then you can only have decreasing exponential solutions here and decreasing exponential kind of solutions here. And taking all these considerations into account, as well as using the connection formula that we had derived before, we actually can easily show that this particular quantization principle follows. The cyclic integral of p dx over a complete cycle divided by 2 pi, the so-called action integral, turns out to be n plus half times h bar. This is a celebrated Bohr-Sommerfeld quantization condition that we introduced in a previous lecture. This, of course, was one of the leading lights in old quantum theory, and quantum mechanics via the JWKB approximation gives us a justification for this. It also gives you an additional correction term of the half which was missing in the original Bohr-Sommerfeld quantization principle. Now, let us go ahead and talk about the normalization of this particular wave function in the WKB approximation. Of course, the normalization would actually have to be such that when you take the mod square of the wave function and integrate over the entire real line, you should get 1. However, if the turning points are A and B respectively, the sinusoidal wave function between the two turning points actually contribute a major part. Beyond the turning points, the wave function decreases exponentially in both sides. So we could often just ignore that contribution. What we end up with is approximately an integral of chi mod square between A to B, and if you use a WKB approximation in that interval, you get c square times c being the normalization constant times dx by p. Remember, you had a 1 by root p in the WKB approximation. There is a square of that. You get a 1 by p times cosine square of this particular integral. And the next step would be to assume that at least for a highly excited state, since there are a large number of nodes between the two turning points, the function oscillates very, very rapidly, and cosine square, when it oscillates rapidly, can be replaced by its average value of half. Once you do that, you end up with c square by 2, the 1 by 2 of course coming from the average of cos square, times the integral of from a to b of dx by p. Just note that p is mass times velocity, so if you just take the m out of the integral, you end up with an integral of dx by v from a to b. Now notice, dx by v is nothing but the time it takes the particle, that is in the classical picture, to cross the interval between x and x plus dx. So when you integrate that from a to b between the two turning points, all you get is the time it takes for the particle to complete 1/2 of the total oscillation. It's just one thing, and hence this quantity is simply nothing but capital T by 2, where capital T is the time period. So what we get is this normalization condition, that the normalization constant c is given by this relation, the c square into t by 4m has to be 1, or you can rewrite this to give you c equals twice root over m by t, or root over 2m omega by pi. So when we actually use WKB wave functions, we resort to this particular kind of normalization. It's not exact, but it's pretty close to being an exact normalization. Let us now turn to a few applications of the WKB method. We will first take a look at the applications that we can derive basically using the Bohr-Sommerfeld quantization condition. Our first example is our old friend, the simple harmonic oscillator. And it should not come as a surprise that the WKB method works rather well here. Of course, the potential V of x for this particular problem is simply half m omega squared x square. And this is something which we have also learned in high school physics. The momentum as a function of x is simply given by m omega times square root of a square minus x square, where A is the amplitude of the motion from the classical point of view. A is also, of course, a location of the turning point, and the energy of the particle is related to A simply by E equal to half m omega square A square. Now, if we make use of the Bohr-Sommerfeld quantization condition, we have to set this particular integral equal to n plus half times h bar. Now, if you put in the value of p, that is m omega square root of a square minus x square, you have to integrate this from minus a to plus a. Let me just correct these two limits. This should of course be from minus small a to plus small a. Now, the obvious thing to do while evaluating this integral would be to substitute a sine theta for x, and if you do that, the integral becomes a very simple one. It's pretty straightforward. Once you evaluate that integral, you end up with half m omega a square times pi by 2, which, using our relationship between E and A, is simply E by omega. This works out to be n plus half h cross. So we see that for a particular n, the energy E works out to be n plus half h cross omega, which is the exact result. So in this case at least, the WKB approximation gives you the exact result for the energy eigenvalues. Of course, it would be too much to expect the WKB approximation also to give you the exact wave functions. We know for sure that the approximation breaks down badly close to the turning point. But let us just see how good this approximation is when you are away from the turning point. So what we will do is we will actually calculate the wave function using the WKB approximation as well. And the calculation of the wave function is rather straightforward. All you need to do is figure out the W bar a comma x function and W a comma x function for the two cases where x is more than a and x is less than a. I'm just going to work out the situation in the positive x part. The negative x part can be treated very similarly, but you can also use the fact that the wave functions are even or odd to fill in the blanks there. So W bar a comma x is simply this integral where you use twice m times e minus v of x, half m omega square a square minus x prime square. That would be the case for p, but this is p bar, so you'd have to reverse these two things. Remember, x prime is more than a here. So you use this, a very simple substitution that immediately suggests itself is x equal to a cos lambda cosine hyperbolic. And if you put that in and carry out the integral, which is sort straightforward, elementary integral, you end up with this result. So your wave function turns out to be some constant by 2. I've deliberately put in the 2 here. Remember, we are on the right of the right hand turning point. That means we have to have a decreasing exponential function. So although the WKB approximation would have allowed both plus or minus sign here you have to put in a minus sign. This integral, being an integral from a to x of a positive integrand, is definitely a positive quantity. So this sign here ensures that as x goes very far away, this solution dies out. So you have a decreasing exponential, and then you have a 1 by p bar x square root. That's part of the WKB approximation. You have a constant in front, and in order to make usage of the connection formula easier, I have written the constant as c by 2 instead of c, simply because there is an extra half in the connection formula for decreasing exponential functions. So this is the solution to the right of the turning point at x equal to plus a. On the other hand, when x is less than a, now the momentum is real, so you use px equal to m omega square root of a square minus x square, plug it into the expression to find out w a comma x. You get a very similar looking integral, except that you have square root of a square minus x square instead of square root of x square minus a square here. And now the immediate substitution to use would be x equal to a cos theta. And now when you integrate this, you're going to get this final result. Now, let me point out once again that this integrand, the integrand for w a comma x, this quantity is definitely positive. However, when you're doing this integral, the upper limit is less than the lower limit, so the integral definitely is negative. And so when you use the connection formula, you have to be very careful. The connection is between c by 2 root over p bar, a decreasing exponential on one side, and c by root p, no 2, cosine of mod wa comma x minus pi by 4. So for the mod w, all we have to do is get rid of this minus sign, because we already know that in this case wa comma x is negative. So minus wa comma x is the positive quantity. So this is the WKB wave function on the left hand side of the turning point. Now to see how good or bad the WKB approximation is, I have plotted a few graphs for you. So the graph that we have plotted here are basically graphs of the WKB wave function for different values of n. The one on the left here is n equals 0, then you have n equals 1, n equals 2, n equals 3, 4, 5. And the blue colored curve is the exact wave function, the one which we had derived earlier using the Hermite polynomials times an exponential drop-off. The curve in green is the WKB approximation. Notice that in each of these curves, you have the function shoot off to infinity at certain points, symmetrically placed points. Those are exactly the turning points. Notice that the WKB approximations are actually quite good when you are far away from the turning point on both this side and in the classically allowed region. However, when you get close to the classical turning points, the WKB approximation fails rather drastically and shoots off to infinity. But that is something only to be expected as long as you are far away from the turning points, both in the classically forbidden region and the classically allowed region. The WKB approximation fits the actual solution rather well. As the next example of an application of the Bohr-Sommerfeld quantization principle, we are going to consider a problem which cannot be solved exactly, unlike our previous example where we knew the exact solutions. This is the case of the quartic potential. V is given by G, some constant G by 2 times x to the 4. And if you plug this back into the Schrodinger equation, you end up with minus h cross square by twice m d2 psi dx2 plus half g x to the 4 psi equals E psi. Now this particular equation has a lot of constants floating around. So we will do what we have done for all such cases. We will change our independent variable x to z, where x is given by lambda z, and we will choose lambda in such a way that our equation simplifies a lot. So once we plug x equal to lambda z into the Schrodinger equation, we end up with this particular version of the equation. Now, if you divide the whole equation through by lambda to the power 4g, it's pretty easy to see that a choice of lambda given by the 6th root of h cross square by mg is going to substantially simplify the equation. At least it will substantially simplify the coefficients here. And you will end up with this version of the equation, minus half d2 psi dz2 plus z to the 4 by 2 psi equals epsilon by 2 psi. Epsilon is simply nothing but what you get when you divide E by lambda to the 4g, and once you substitute this particular value of lambda that we have used, we find that epsilon is proportional to E with an additional factor thrown in. So once you find out epsilon from this equation, the energy E will immediately follow. Now, to find out the energy epsilon, what we use is a standard, by now standard, Bohr-Sommerfeld quantization condition. And here, this particular equation takes the form n plus half equals 1 by 2 twice pi times our momentum px prime dx prime integral between the two turning points. And here, the turning point will be, of course, where the potential energy z to the 4 by 2 equals the energy term epsilon by 2 here. And this will ultimately end up giving you for the turning point as epsilon to the power 1/4. Of course, the turning points are at minus a and plus a, and so you have to integrate this quantity, which is essentially p of z between minus a to plus a. Now, This obviously cries out for the substitution z by a equals zeta, and if you make use of that, it is pretty straightforward to rewrite this equation in this form. And so now, apart from some obvious factors 2 by pi times root over epsilon times a, this part depends on the energy. You have an integral which does not depend on the energy at all. This is the integral from 0 to 1 of square root of 1 minus zeta to the 4 d zeta. Now this integral can be put into a very familiar form just by using the substitution zeta to the 4 equals t, and that, after a very simple manipulation, gives rise to what is called the beta function. So apart from this 2 by pi root over epsilon a, you have this quantity which we call the integral I, and that's essentially 1/4 of beta function with 1/4 and 3 by 2 as the two arguments. You can express this in terms of the gamma functions if you want, and then look up the table for gamma functions or use your favorite programming language to find out what that gamma 1/4 is, and this will ultimately give you a value for the integral of around 0.874, something of the order of 1. And now, since we know that a is related to epsilon as epsilon to the power 1/4, we can use that to find out the energy for the nth level, at least the epsilon for the nth level. You can translate that to the energy very simply, and this is the expression that you get. Now let me point out that here we do not have an exact solution to compare our WKB result with, but it is guaranteed that the WKB result will become better and better as the system gets closer and closer to classical, or strictly speaking, as the system gets to a situation where h cross can be roughly ignored. That of course happens at very large n. So you expect this particular predicted behavior, basically apart from a constant is n plus half to the power 4/3, will be followed rather well for highly excited states. It so turns out that we can actually compare these energy eigenvalues that we obtained by using the WKB method with energy eigenvalues obtained by using some kind of numerical method, let's say the shooting method. And if you compare the two, you will find that not only does the approximation become pretty good for large values of n, even for small values of n, the WKB approximation gives you a result here which is not exact, but which is pretty close. Let us quickly discuss a situation where the potential is defined only for positive x. You have solved problems like this before. For example, you have talked about a harmonic oscillator, rather a half harmonic oscillator, where the potential energy is half m omega squared x squared for positive x, but infinitely large for negative x, which essentially means that in all such problems, the wave function vanishes at the origin. Now here, application of the WKB method is pretty straightforward, and this gives rise to a slightly different version of the Bohr-Sommerfeld condition. All you need to do is start from the fact that to the right of x equal to a, where x is bigger than a, you are in the forbidden region. You have a decreasing exponential e to the minus w bar a comma x with c by 2 root p bar as a coefficient, and this will connect up according to our connection formula with c by root p cosine of w x comma a minus pi by 4. The only important thing is that in our classically allowed region, x is less than a and x equal to 0 falls in the classically allowed region. Since psi 0 has to be 0, cosine of w0 comma a minus pi by 4 must vanish, and this immediately gives me w0 comma a minus pi by 4 is n plus half times pi, and this gives us w0 comma a equals n plus 3/4 of pi. So this essentially becomes equivalent to our Bohr-Sommerfeld quantization condition. w0 comma a is basically the integral from 0 to a of px x dx up to a factor of 1 by h cross. So what this is really telling me is the integral from 0 to a of p of x dx is equal to n plus 3/4 pi h cross. Now I mentioned the solution for the half harmonic oscillator a while ago. And if you remember how you solved this in an earlier class, you would definitely recognize this particular method that I'm going to talk about now. All we do is we pretend that the potential is actually an even potential by extending it to negative x as well, by defining v at minus x to be the same as v at x. Then of course the Bohr-Sommerfeld condition simply becomes w from minus a to plus a, those are the turning points now, must be equal to m plus half pi, where m is some integer. But the condition that psi 0 equal to 0 implies that you must only consider odd solutions for the wave function, and that means m has to be an odd number twice n plus 1. So w minus a to plus a, which is twice w of 0 comma a, given the symmetry of the potential here, must be equal to twice n plus 1 plus half pi. All we have done is replaced m, which is an odd integer, by 2n plus 1. And this immediately gives us back our result, which we derived a while ago. W0 comma a must be n plus 3/4 pi. So both ways of thinking about the problem, one by directly applying the WKB wave function behavior, and the other by modifying the potential to be an even potential and then applying the Bohr-Sommerfeld conditions, gives us exactly the same condition. You can use this particular Bohr-Sommerfeld condition for this case to figure out solutions for many different problems. One very important field of application for these results for a potential defined only for positive x happens to be the case of spherically symmetrical potentials in 3D. As we have seen before, in such a situation, the radial part of the wave function capital R of R can be replaced by a related quantity u of small r, which is capital R divided by small r, and that quantity obeys the Schrodinger equation, which is exactly like the Schrodinger equation of particle in one dimension, except for two things. One, in addition to the actual potential energy, there is a centrifugal barrier term in the potential energy given by L into L plus 1 h cross square by twice mr square. And the other major difference, of course, is r can go only from 0 to infinity. So this is exactly the same situation as the one we made just now. Here P of r will be simply square root of twice m E minus the effective potential, that is the potential V, in addition to which you have this centrifugal barrier potential. Using this and the modified Bohr-Sommerfeld quantization condition that we worked out just now, you can actually figure out estimates for energy levels for various problems. Sometimes these estimates turn out to be astoundingly good. However, given the fact that the potential energy actually rises rather rapidly in this case, at least as r goes to 0, because of the 1 by r square term, or because the potential energy itself may have a singular behavior at r equal to 0, you may wonder about whether the WKB approximation is at all valid there. And that is quite a legitimate concern. So let us take a look at that now. Recall that the condition for validity of the WKB approximation, modified here by simply replacing x by r, happens to be ddr of h cross by magnitude of p must be much less than 1. I'm talking of magnitude of p because p may be purely imaginary, as is the case in the classically forbidden region. Now, if we consider the potential energy to be something which obeys a power law kind of behavior and blows up as r goes to 0 like r to the minus alpha, then close to the origin, mod p will be dominated by this term, provided alpha is large enough, and mod p will turn out to be square root of twice mc r to the minus alpha by 2. So for the WKB approximation to work, you must have 1 being much bigger than h cross by square root of twice mc ddr of r to the alpha by 2. Essentially, you get 1 is much bigger than a bunch of constants times r to the alpha by 2 minus 1. Now, as long as alpha is bigger than 2, we are fine with this condition as r goes to 0. On the other hand, alpha bigger than 2 is exactly what you want for our conclusion about the behavior of mod p to really work, because if alpha were less than 2, then the centrifugal potential barrier term L square by twice mr square will dominate, except in the situation where small l is 0. So, if alpha is less than 2, L into L plus 1 h cross square by twice m r square will dominate, and then mod p will simply be given by square root of h cross square by r square L into L plus 1 when you're very close to the origin. So mod p will be basically inversely proportional to r. And now the WKB validity condition simply tells you that 1 must be much bigger than 1 over square root of L into L plus 1. What this means is for the WKB approximation to work fine, you need to have a very large L for this case. So either the potential has to be rather sharply varying, that is, should go like 1 by r to the alpha with alpha bigger than 2. That's a bit counterintuitive given what we have always thought about the WKB approximation's basic demand. Or you would need L to be very large. In these situations, the WKB approximation would work fine. Indeed, the behavior of the wave function predicted by the WKB approximation, done naively, turns out to be pretty bad. It does not actually match the behavior that you would expect from the fact that you have a singularity of the form L into L plus 1 by r square. Langer had worked out a way of converting the radial coordinate into a new coordinate which actually extends all the way from minus infinity to plus infinity, and had used that in conjunction with the WKB method to derive a corrected version which is valid for this case. We will not go into the details of it here, but you can read up the Langer correction on the net or in your textbook if you want to find further details. Let me wrap up this lecture with a rather little known but quite important result from WKB theory. A list of applications of the WKB method literally runs into hundreds, not only within quantum mechanics, but even in other branches of physics where differential equations play an important role. But even if we stick to just quantum mechanics, it will not be possible for me to talk about all possible applications of the WKB method. So I will have to pick and choose. The one topic that I will talk about right now is the connection of the WKB method with our standard perturbation theory. And this is a slightly less well-known application of the WKB method. But what I want to show you here is that using the WKB method, you can reproduce the results of first-order perturbation theory rather accurately. And as in all situations with the WKB method, the approximation gets better and better for higher and higher values of n. That is, the closer you are to the classical scenario, the better the WKB method is going to be. Now the setup of our problem, we will now expand the integral on the left-hand side, keeping in mind the fact that since delta V is small, delta En, delta A and delta B are also small. So what we will do is we will retain only first order terms in terms of these small quantities. Now the first thing that you should notice is that the effect on the integral of the fact that the limits have changed, that A has become A plus delta A or B has become B plus delta B, will actually vanish if you only consider first order effects in small quantities, because that effect essentially is delta B, for example, times the value of the integrand at x equal to B. Now the value of the integrand at x equal to B is 0 if you ignore the first order correction term delta En minus delta V. After all, you are at the turning point, and at the turning point the momentum vanishes. By a similar argument, you can also show that delta A will not contribute anything to the first order. So the first order energy correction to the integral will only come from the integrand itself. Now in the integrand, twice m into En minus V is nothing but the momentum function for the unperturbed potential. Let us call that P0 of x. So if you do that, you can write the square root as the square root of P0 whole square, that of course is twice m into En minus V, plus this additional correction term which is small, twice m into delta En minus delta V. The obvious thing to do would be to pull out P0 from the square root, and then you have 1 plus a small quantity raised to the power half, so you can immediately use the binomial theorem and retain only the first order terms in delta V. If you do that, the left hand side is essentially going to be, you can actually ignore the delta A and delta B here. We have already argued that there will be no effect because of that. It's going to be P0x, that's the P0x into 1, the first order term in the binomial expansion, plus m into delta En minus delta V by P0x plus higher order terms, integrated from A to B, is equal to n plus half pi h cross, which is also the value of P0x dx integrated from A to B. This is nothing but the Bohr-Sommerfeld quantization principle applied to the unperturbed situation. Of course, the two integrals over P0x simply cancel each other out from the two sides, and you are left with this expression. The integral from A to B of m times delta En minus delta V by P0x dx is 0. This can be easily broken up into two integrals, one involving delta En, the other involving delta V, and delta En being a constant can be easily moved out of the integration. And once you do that, what you end up with is this simple result. The integral that involves delta En is delta En. Delta En being a constant can be moved out of the integral, and this gives rise to delta En times an integral from A to B of m dx by P0x. Notice that's nothing but dx by velocity, and hence the integral on the left here is simply delta En into capital T by 2. On the other hand, on the right hand side, you have the integral from A to B of m delta V dx by P0x. So you can easily rewrite this to give you delta En as 2 by T times the integral from A to B of m delta Vx by P0x dx. Notice that dx by P0x into m, this quantity is nothing but dx by V. So that essentially tells you how much of its time the particle spends between x and x plus dx. So what you have really done is multiplied delta Vx by the time the particle spends close to x, summed it all up, and then divided by the overall time, which is T by 2. This, of course, is exactly what a time average is. So the final result that we have from the WKB method is delta En, the energy shift due to perturbation, turns out to be nothing but the time average of the perturbing potential over a classical orbit. The connection between this result and the Rayleigh-Schrodinger perturbation theory result that we had derived earlier should be pretty clear. Here what we are getting is delta En, the energy shift that is predicted by the WKB method, is a time average over the classical orbit of the perturbing potential energy. Whereas in the Rayleigh-Schrodinger perturbation theory, the first order energy correction is nothing but the expectation value of the perturbing potential in the nth energy eigenstate. So this is sort of mimicking the time average versus ensemble average picture that we have in statistical mechanics. Let us now turn to an application of this particular result. We will try to use this method to predict how much the energy will shift for a quartic perturbation on top of a harmonic oscillator. So if you have a simple harmonic oscillator, the standard simple harmonic oscillator, with an extra perturbing potential of lambda extra 4 applied on it, according to the WKB formula, the change in the energy delta En must be simply 2 by T times the integral from minus A to plus A, the classical turning points, of the perturbation lambda extra 4 dx divided by the velocity. And the velocity, as you all know from classical mechanics, is omega square root of a square minus x square. Now this integral can be evaluated pretty readily, and the answer turns out to be 3/8 of lambda a to the 4. And using the fact that A, the turning point, is related to the energy by half m omega square a square equals En, which is of course in turn equal to h cross omega n plus half, we can find out the value of a square and then square that and plug it into the expression for delta En. And this gives us the following expression for delta En. Delta En is 3 lambda by 2 times h cross by m omega whole square times this independent factor, which is n square plus n plus 1/4. Now this agrees very well with the first order perturbation result from the Rayleigh-Schrodinger theory. In fact, this agreement becomes very good at large n. The Rayleigh-Schrodinger perturbation theory result is very similar, except that instead of n square plus n plus 1/4 in the bracket, what the perturbation theory would tell you is that the bracket is n square plus n plus half. So for large value of n, of course, these two results are very close to each other, because the difference between 1/4 and half can simply be ignored when n is large. But even for small value of n, say n equals 1 or 2 or 3, the agreement between the perturbation theoretical value and the WKB approximation is quite striking. But I would again emphasize that WKB, essentially is a semi-classical approximation, works best when you're talking about large energies, that is, at least highly excited energy levels. And that is something you can see even from this particular application. In the next lecture, we will explore this connection between the WKB method and the classical limit in a bit more detail. We will also take a look at one of the most important applications of the WKB method, which is in trying to figure out the tunneling probabilities for tunneling through a barrier which has an arbitrary shape. Remember, in your elementary quantum mechanics classes, you had learned that a particle which is classically forbidden to go into another region can still manage to go through. But there the calculation that you did was based essentially on rectangular barriers. We will see how we can adapt that to arbitrary potentials via the usage of the WKB method. This actually was one of the first major triumphs of quantum mechanics, because Gamow managed to use this technique to work out a theory of nuclear decay, in particular alpha decay of radioactive nuclei. We will also take a look at a few other applications of the WKB method next. Goodbye for now.